And cool. We can see your screen.
Okay, awesome. Yeah, thank you. Thank you, Ria and Madhu. So, yeah, thanks everyone for joining. Today, I'm going to talk a bit about agents and the entire journey of how they progress, how the field progressed from the time I joined industry. And we're going to cover like a bit on some of the fundamental pieces of technology that enabled this kind of agentic sort of environment to develop over the years. So yeah, I'll just quickly start off with my background. I am a UW alum. I majored in data science and minored in UX. I graduated in 2018. I've been in the AI ML space from over 7 years now. I'm an applied scientist, and I work on some I worked on some applications related to supply chain optimization, content moderation, optimizing ad pipelines, and more recently agentic systems. I'm a brand new New Yorker. I just recently moved to New York this Jan. So most of my work has been in NLP, and I've kind of been close to the evolution of the different technologies that kind of evolved into the agentic era that we are in right now. So just to outline, I'm going to track this journey of the field over three distinct periods, like 2018 to 19, 2020 to 23, and 24 onwards. Introduce reasoning models and then agents, and then we'll talk about some applications and use cases, and then design considerations and challenges that we face with deploying these kind of systems, and then my thoughts on the future of work. So 2018-19 was a time when models were highly specialized. We had very specific models that do specific things. For example, you had a sentiment detection model or a text classification model, a summarization model, a question answering model. So for each type of task, you had a different model. You had to train them, build them separately, own and maintain them, and it was very effort intensive. And we kind of learned at that time early lessons that instead of creating models that have custom features, uh, custom logic applied to them, we are better off scaling the compute and data, and applying more compute to the training process and giving these models more data to get more predictable improvements in like the performance. So this was a time when it was a year right after the transformer attention is all you need paper had come out, and there's an explosion of transformer based models. This was the early GPT 2, GPT 3 era. And we learned this bitter lesson, which is it's called the bitter lesson. It's a very famous paper by Richard Sutton, and he talks about how general purpose methods that leverage computation and apply more data to the model training process generally outperform like human designed manual feature engineering, those kind of things. And attention was also like a very parallelizable and scalable training method, which could be trained across several GPUs. So so after this phase, we saw this phase where models just started getting larger. We started putting more data, more compute towards the models. We started building larger models that went from like few million parameters to few billion parameters, and now we are almost at a few trillion parameters. So models got larger, they were more aligned to human preferences, and they were instruction tuned. So they were tuned to follow instructions. Um, so here the models started um, adhering more closely to human instruction. They started following uh, through RLHF, they started following human instructions better, and then they also started following uh, they became more general. So you could have one model that does multiple things. You didn't need separate models like for each specific task. So one model could do translation, could do summarization, could answer questions. And then this whole prompt engineering space kind of exploded. And chain of thought is one of the very key kind of prompting techniques that I want to talk about that really improved the performance quite a bit. So chain of thought, for those who are not familiar with this, it's basically a way where you input the logic and the reasoning and the steps to solve a problem into the model's context window. So here, from the paper, you can see the blue highlighted part where, there's a math question, and then you tell the model exactly what kind of steps you need to take to get the answer. So you're showing your work to the model, and then the model performs much better when you do this. So it improved the model performance on uh, math tasks, on symbolic tasks, common sense reasoning tasks, and this prevents the model from like just shooting from the hip, giving like hallucinated answers that are not valid. So here you can see like the blue lines from the paper, the performance after chain of thought improved quite a bit. So in this stage, we were still giving these instructions manually, and one of the lessons was that yeah, giving these reasoning the steps to solve the problems to the model actually helps them do better. And I just want to briefly talk about this system one, system two thinking. If you read this book by Daniel Kahneman, he's a Nobel Prize laureate, who talks about these two ways of thinking: the slow, the slow thinking and the fast thinking. So system one is like when you have very intuitive, emotional, gut feeling answers, and system two is when you have slow, deliberate thinking, consciously solving problems. Uh, it's a bit like more energy intensive, but it's more reliable. So the similar parallel you can draw with the transition from the early LLMs, which were like pattern matching systems, which got very good at understanding how language works and completing sentences, to models that can think and respond by working through the steps of the problem. So this first paradigm from like 2018 to let's say 23 was like the strain time scaling paradigm where there was this conscious effort to increase the model parameters, increase the amount of data for training, increase the compute, and that worked well for some time. We realized that more data. Eventually, it kind of capped out because there's all this internet data, and a lot of the internet data is not very useful. So slowly, people began to shift towards collecting better, higher quality data to train these models, and then optimize the compute. So, so there's this other paper that talks about like chinchilla optimal models. So the researchers realized that some of these models they're being super undertrained. So the number of parameters you have relative to the amount of data you're giving the model to learn, the model is actually undertrained. So it's not actually picking up all the characteristics of the data. Uh, and they arrived at like a specific relation between the number of parameters a model has and how much the size of the data should be to train that model for a fixed amount of compute budget. And so from their research, they found that, like a 70 billion parameter does much better than a 280 or 175 billion parameter model. By optimizing the amount of compute and data they give this model. So they arrived at this 20 tokens per parameter optimal kind of relationship. And models right now, they're trained around like 13 to 40 trillion tokens, each of these models. And the public limit of data available publicly on the internet is around 300 trillion tokens. So if you divide that by 20, you get to around like a 15 trillion parameter model. And the current state of the art, like the largest model right now, openly declared weights is like a 1 trillion parameter model. So this kind of led kind of to another kind of realization, another wall where, we can't keep throwing data and compute forever to make these models better. And there's probably some other alternative approach that eventually we are going to run out of this high quality public data. And the larger you increase the parameter size of these models, it becomes harder to maintain and run them and costlier to run them. And there's other practical problems. So there's this other paradigm called test time scaling. So instead of the train time scaling, where you train the model a lot longer on much larger data sets, you instead of doing that, once you train a model, you spend more time on the inference part. So you generate more inference candidates, generate more answers, and then pick between those answers. So this is one of the kind of shifts. So chain of thought was one shift. This is another shift. So here you can see how um, the models are generating this thought process. So if you use Chat GPT, you see like thinking like a section when you can expand it, and that's this whole part here. So we started uh, asking the models to generate more thought processes, like think about how you solve the problem, think step by step. And then there were different ways in which you could scale this test time scaling. Like one way is like a sequential method where you keep generating one thought after the other. And the other way is a parallel kind of method where you ask the model to generate multiple candidates at once, and then you maybe take a majority vote between them. So, so this is kind of similar to like system one, system two, where the early LLMs were like just trying to complete a sentence, just trying to give you an answer really quickly. And system two is where you ask them to think more during inference time, generate more candidates, and then you evaluate them. So this was more deliberate. And then the next thing that happened was uh, the researchers, they started doing reinforcement learning on the thinking traces, so on the chain of thought. So this is kind of an example of the training data. So here you have a solve an equation, and the bold text here has 3 steps, and then you label each step where you say, hey, this step will lead you to the correct answer, or this step will take you away from the correct answer. So, so it was kind of like a self-corrective, self-audit on the thinking process of the models, where you could train the models to follow the right direction towards getting the answer. And once you have this reward model trained, you start generating these steps, and the reward model tells you if the reward is high, that means the model is going in the right direction. If it's low, then you ask the model to generate another answer. So you go back to the loop, ask the model to generate another answer. So this is like a process reward model, where there like with this labeled step by step data, where the chain of thought itself is labeled, the models became aware of what kind of trajectory to take to answer a question. So just to recap, like 2018 to 23, we had this foundation of really strong models that were aligned to human preferences, that were trained optimally, using the optimal amount of compute and data. And then we had this self-correcting reasoning process where models could correct their own thinking. Um, so this was kind of the shift from like the generative to the reasoning, this text completion generation to the reasoning phase. And 24 onwards, models went beyond generating just generating language. we started relying on this refined reasoning patterns to drive code execution. So that's where we enter the agentic era, where the focus is not just on acting or the focus is not just on reasoning and completion, but rather on acting through executing code. Uh, and context engineering takes priority, how you exactly fill the context of a LLM at any point in time. And then orchestration of these LLMs with complex external capabilities became important. Tools and MCPs give additional capabilities to these models to take deterministic actions. And and there were like communication protocols, like agent to agent communication for agents to communicate with each other. So I'm going to maybe just talk about another like technique called React, which similar to chain of thought, but there's another element of taking a certain action, which was kind of a early kind of seedling of agentic AI. So here the model follows an iterative cycle of think, act, and observe. So wherever you see the arrow, so here it's kind of like a complex, convoluted question. So aside from the Apple remote, what other device can control the program Apple remote was originally designed to interact with? So so here first you need to know what other devices uh, does are related to the device that the Apple remote also controls. So it's kind of like a multi-step thinking. And here you can see in the act step, there is a search call. So the search searches the internet and then gets some answer. That's the observation. And then you again repeat this like multiple times. So the LLM keeps getting these answers, keeps refining its thought, and then acts and then has another observation and then refines the thought. And it keeps doing this repeatedly till it gets the answer. So this is kind of like the foundation of tools, and tools are uh, external capabilities that are defined as a schema, as a JSON schema, where you have a name, a description, what do they do, and what kind of inputs do they take. And these are injected into the LLM's context for the LLM to then give you a structured function call signature. So the LLM does not really execute any code, but it gives you like how to exactly call a function with what kind of inputs, because it has this tool definition in its context. So here's like a quick example where you ask what's the weather in Paris, and then the LLM uh, before this question goes to the LLM, the LLM also has some tool definitions in its context, and it knows that, hey, I need to ask get weather to get this answer. So the LLM will provide this JSON output, which is get weather, location is Paris, and then the orchestrator takes that JSON, runs that code, and gives the answer back to the LLM to generate the final answer, which is step 4. It's 15 degrees Celsius. So, so this is like orchestration. So the LLM knowing how to call the tools, what are the input parameters. It takes an unstructured language question and then gives like a structured function call, which is then run by an orchestrator to basically interact with external systems. So so this kind of became kind of a way of giving LLMs extra capabilities for some time till it became a problem, because everyone was writing custom tools uh, to give these external capabilities, but every time you write a tool, you need to write this tool again for another model, or if you have another app, you need to kind of define it again for that model and manipulate it separately. And if you have n models, m tools, you go into n by m integrations, which became very difficult to maintain. And the code became very fragmented. So MCP came in where you register all your tools in a single place. There's a client, which is your orchestrator, and a server, which is the MCP server, where all the tools are registered, and you just need to register them once. And if your orchestrator can access the MCP, it will have access to all the tools within that MCP. So this helped streamline the things a lot. And then this is like the procedural orchestration of LLMs, which is instead of um, just running an LLM, getting an answer, you manage the LLM's execution with a program. So prompt chaining is a very like simple example where you take the given input to an LLM, you get an output, and then you give that output to another LLM as an input, and then you get that output, and then that output is your final answer. So an example could be, analyze a 50-page doc, write a summary, and list 10 action items. So you're analyzing the 50-page doc could be an input to the first LLM, and then that output goes to another LLM as, write a summary for this, and then that goes to another LLM, just list 10 action items. So this kind of enabled creating more complex functionalities without overloading a single LLM, because if you give a lot of um, tasks to a single LLM, there could be subcognitive load, and it can become unreliable. So this was a more reliable way of doing things by chaining them together. Um, and then memory is another element where there's different types of memories, but this is basically how you give additional information to the LLM to give more grounded, factually grounded answers. For example, an LLM doesn't know something about a new business domain, or let's say you use a very specific acronym in your business, and you ask a question, what is the specific LMN, whatever thing. So this will be added to the LLM's context at runtime based on maybe some long-term memory, and then the LLM knows what that means. And there's obviously this limitation of context window too, where LLMs can't really uh, take in the entire data in the context. So this is a way of like strategically managing the LLM's context, and we'll probably talk a bit about this. So just to recap, we had uh, the shift from reasoning to reasoning and acting, and then there's dynamic context and memory involved, and then there are tools, and there's a system orchestrating between all of this. And this is test time compute, because you're like relying more on inference versus training. Your model is already trained, and you're relying more on inference to create more complex capabilities. So I think we could maybe just think of defining agents right now. So agents are basically autonomous systems powered by LLMs, which are the brains, and they use planning, reasoning, memory to break down uh, complex goals into simpler kind of tasks and execute multi-step actions using external tools. So there's like a planning and reasoning component, memory, action, orchestration, and then tools. So this kind of is like the foundation of agents, and then a lot of the work is about how you piece these things together, how you design different mixtures of these individual components to solve whatever you're trying to solve. So one very common pattern is agent RAG, where uh, because your LLM has limited context, and you want to answer questions on some very specialized knowledge. So you give the agent access to this knowledge source, could be a set of documents or a database. And then every time you ask a query, which is the number one here, uh, you you can have a vector index or a vector querying logic that would just take the relevant documents that are related to your query, give that along with the original query to the LLM. This is number three, the prompt and enhanced context, and you generate the response and then send it back to the user. So this kind of solves a lot of like complex question answering cases. Another pattern is a tool-based agent where you have an orchestrator, you have an MCP server where a set of tools are registered, and these tools can do an number of things like deterministic tasks that the LLM is not capable of. So every time you ask a query, first the orchestrator goes to the MCP server and then gets a list of the tools, sends the list of tools and the query back to the LLM, and then the LLM decides if it needs to call a tool to answer the question. Uh, if it does, it will give the JSON as we discussed, and then execute that, get the result, give it back to the LLM, and then generate a answer. So this is like one very common pattern. Coding agents, I don't know if you guys have tried Cursor or some other coding kind of tools, and these are also very similar. So here the IDE gives some context of the environment along with the query to the LLM. The environment context can be anything from like your the file structure of your folders, your package.json, what files are open in your IDE, what kind of dependencies are there in your code base, and then it passes that along to the LLM. And then the LLM does the reasoning model that's been like trained on chain of thought. It does the reasoning, writes the code, sends it back, and then the IDE does those edits, and then you see your code being written. Um, Another pattern is like a parallelize aggregate pattern. So this is when you just want to split out um, input to different LLMs. Maybe you want to run something in parallel, and each of these tasks is not dependent on each other. Like let's say you want multiple perspectives on a question, you want to explore it in parallel. So you can send it to each LLM separately, let them generate their answer, and then send it back to a final LLM that aggregates all of them and gives you a final answer back. Um, Orchestrators. So here, instead of just sending it to every LLM, you ask an LLM to decide where to send it to. Like if you need to assign different responsibilities and send like a question maybe sometimes to the first LLM, sometimes to the second and third LLM. So you can split that up and then create more complex kind of answers, complex kind of solutions, complex solution paths. So this could be something like that mimics how human teams work, where you have a manager that coordinates between two or three, four or five employees and gives a task to two of them to like go and figure out a project. Um, this is kind of one pattern. And there's several more patterns. I would recommend this document that I have here, which has a list of patterns. And I think every pattern has its own unique kind of characteristics. So you have to decide which one to use based on what you're trying to solve. Um, and yeah, agent to agent is so each of these patterns, there are several libraries that can implement them. There's like LangChain, there's Strands agents, there's LangGraph, there's Crew AI. So MCPs typically help each agent get the tools that they need to solve the problem. Let's say you have two separate agents and they're both implemented using different kind of frameworks, and but then you want those two agents to talk to each other. So that's kind of where this A2A protocol that is an open standard helps. So this creates like a standard kind of communication method between two black box agents that have totally different internal implementations, but then you want them to go and talk to each other. Like, for example, one agent could be like a travel agent, and then another agent could be a flight booking agent, and then a third agent could be a hotel reservation agent. And each of them are owned by different companies. Each of them have different internal implementations, but then you want them to talk to each other. So A2A is kind of what facilitates that. Um, so some of the design considerations from my experience working with agents, like I would say, like start with something that's a narrow, high impact workflow, something that's repetitive and takes a lot of time, and no one likes doing it, like it's boring. So maybe that's kind of your initial stab at trying something agentic, rather than building like a general purpose, large multi-agent AGI. So yeah, just start small. um, Keep the human in the loop for like high stakes decision. So there's like a precision complexity kind of matrix where you have something that needs very precise answers, or less precise answers, and something that's very complex, less complex. So agents typically thrive well in like more non-linear, complex kind of areas where you have natural language input requirements. You want it to go and figure out a few things and then come back to you in maybe 5 minutes, 10 minutes, and you don't want the answer right immediately. So that's kind of like, if you really wanted to be very precise, you might want to involve a human in the loop to ensure that you get a approval before taking a final step. Keep the tools focused. So sometimes people build a lot of tools, and there could be similar sounding tools or tools that do the same thing, and that will create like like a tool collision within the LLM, and it will get confused between which tool to call. So keep them focused, and very specific, addressing a very specific piece of functionality. Uh, and sometimes the users might ask questions without giving a lot of details. So, but then instead of just like going by some assumptions and trying to give an answer without the complete data, like the agent can ask users for clarifications, like what do you need? Do I have the complete data? And then once you have all of that, then you can trigger like a further kind of uh, solution. So avoid over automation. So sometimes like you don't need agents, you just need a simple like script or a software kind of solution, and you really don't have to build an agent. Um, and you should try to like cap out maybe like a single agent approach with like multiple tools attached to an agent before trying like a multi-agent. Um, because like agents are also expensive, and the more agents you have, the more tokens they consume and the more cost you add to your system. Um, so there are some practical challenges with applying this agentic solutions. So sometimes if you ask the same question twice, you won't get the same answer. And some of these deterministic features are critical for building trust, user trust in the system. For example, if you're generating a financial report and you get two different answers when you ask the same question like back to back, that's not a very good experience. Hallucinations, this could be partially solved with like giving knowledge base to the context. Context bloat is something where there's a lot of context in the agent's context window, and it's not very relevant to what you're trying to solve. And because you're so many steps down the line, there's a lot of context filled up, and it will increase your costs, and it will also confuse the LLMs. Latency issue because these systems are not very fast. Sometimes they take like 5 seconds, 10 seconds to answer a question. So if you want something that runs very fast, then maybe you need to try like a different approach. Cost, uh, it's like, you instead of like when you just have a single LLM generating the answer versus multiple agents calling multiple things and calling LLMs again and again, it increases the amount of tokens that you're like expending, and then increases the cost. So API maturity is kind of important because many of these tools, like for agents to take actions, you need to be able to do those programmatically. But if uh, s- your environment doesn't have enough APIs ready, it becomes hard for agents to do something. So having a landscape where your APIs are mature, you have them mapped out to your business outcomes is kind of important. Measuring and evaluating these systems are difficult. Sometimes you don't know, like, how do you actually measure uh, or evaluate, or sometimes the answers are not like a binary yes or no. So like it's kind of like tricky to evaluate. But you could start with a small data set, maybe 10, 20 cases, make sure that it's working as expected before you roll it out to broader audience. And yeah, permission security. Yeah, there could be a lot of data. There's a lot of data moving around. So ensuring like your trust boundaries are tight, your authentication is tight, data from one session is not going into another session. That's kind of important. Um, so these are some like patterns I've seen from like working in industry and maybe some of the conferences I've attended. So there's this general trend where, because LLMs are expensive, uh, many people are distilling LLMs, larger models, into smaller models. Like let's say a 400 billion parameter model. They get data from this model and then they feed it to maybe a 300 million parameter model. So this is like a way to distill the knowledge from a larger LLM into a smaller model, because it's cheap. The smaller model is cheaper to run and they're faster, and you can host them without it being too expensive. Parameter efficient fine tuning is very popular. So this is when you only modify a low rank matrix versus modifying the weights of the entire large language model. So with this you can do fine tuning in like a few $100s, and you don't have to spend like millions of dollars trying to train a LLM. So this gives like very good results. um Domain specific knowledge. So this is like again like one of the patterns we saw, where you have agents that go talk to knowledge bases and then get that back to the LLM for context, and then improve the quality of the answers that are specific to like domain related question answers. And the data augmented agent. So this is kind of a way to automate data analysis, where you have an agent that writes a SQL query, gets data, and then gives it back to the LLM and gives you an answer based on the data it has seen. So like a very data grounded question answering. And then I think like a lot of these methods, if you see, they're related to making the answer more accurate and more domain specific. So like more predictable. So SOPs again are a way to guide agents towards a very specific path of execution. So you can give the agent an SOP. Hey, this is, if you see this problem or this question, take these steps to solve this, and then follow this plan. And then next time it sees that, it uses that same plan to solve the problem, and then you have a more standardized approach. um, Synthetic data generation. So this has been very useful with a lot of LLMs. So sometimes you have very sparse data for rare events or edge cases, and let's say a healthcare company needs training data for a rare kind of disease, or like a realist. They need to simulate some patient records So you can do this with agents without compromising the patient privacy, generate more synthetic data. Or if you have like, let's say, very few true positives, you can use those true positives to generate similar true positives using LLMs, and use that to tune your models. Um, so coding with AI, I think this is something that's like become a very huge application. If you see some of the tweets from Andre Karpathy, he's the guy who coined the vibe coding term. He said like in November he was doing like 80% of the time writing code, and sorry, it's like writing to reviewing. So 80% of the time he was writing code, 20% of the time reviewing. But now he's like, I do uh 80%, like 20% of the time writing and 80% of the time reviewing. So with AI coding, I think it it's gotten very good. Like it's gotten surprisingly good, and a lot of professionals are using AI to code. Like I personally use AI to code a lot at work, and here I've observed that instead of just giving it vague requirements, it's good to spend some time fleshing out your requirements and your constraints, and then giving this well-defined spec. Like, so think like a requirement, a product manager or something. Give your AI like clear cut directions and what you want to achieve, and what are the different uh, like you can be very specific here, like what kind of modifications you want to do, what kind of APIs you wanted to work with. So that helps test-driven development. So because it's so much easier to write code, it's also easier to write test cases. And I think if you can use AI to write test cases, generate like that constrained kind of verifiable environment where you give it a lot of tests, and then you give it requirements, and then you let it go figure everything out, and then it keeps figuring it out till all the tests are passed. And after that, you know that it's arrived at like a very good solution. So that's kind of useful, and like building more modular code blocks, which also helps humans read the code and understand the code, and checkpoints reverting. So like committing your work before you go off on some experiment, so that you can always come back to your previous working state. So yeah, that kind of helps. Um, so this is how I apply this. I would say like start with a draft. I personally start with a draft instead of directly going to AI and then just asking it to solve everything. There's some research on this that heavy chatbot use may lead to the atrophy of critical thinking skills, from like a MIT paper where they looked at brain activity of people who directly went to AI for getting an answer versus like this the other group that thought something and then went to AI. So I would say like use AI to just refine your draft and critique, and then and then edit the output to, and then apply your own style to it. Um, I think that will keep you a bit more engaged and will also like keep your mind a bit more stimulated for like over the long term. And then there's so many unexplored ideas and quick prototypes that you can do something that you never like explored because you didn't have time. So you can definitely use like AI to like flesh those ideas out for you. So that helps. I use it a lot for like charting and data visualization. So let's say I have a CSV and I want to visualize it a certain way, and I want like a matplotlib script. So I do that a lot where it helps me understand the data better. It definitely saves a lot of time. So writing, like generating visualizations from scratch can sometimes take like half an hour, 1 hour, but this takes hardly like few minutes. So I do use it to update my blog's UI. So all the HTML, CSS, like I don't touch it anymore. Like I just give the requirements to AI, the code agent. Research and learning is very useful, like when you're trying to learn a new topic, do open-ended exploration. And I generally see that people are shifting from writing things and writing code to reviewing, editing, and architecting code. So I think this is going to be something that's just going to be like with us in the future. So I think we just have to be better at editing and reviewing and catching the mistakes of AI and, making it close to your own style. Um, yeah, and yeah, just be aware of overuse and the impact it might have on your own thinking abilities. Um, so yeah, as I said, like there's a shift from doing the work to supervising AI, and as more complex systems get built and more complex agentic applications get built, I think more and more we will like go towards supervising these systems versus like actually doing the things. Uh, and yeah, your work can be highly leveraged. Like you could probably get the efficiency of a whole team in a person because of all this like AI writing. You can write 1,000 lines of code in a day, which was kind of hard to do 3 years ago. So I think the I would recommend this essay too by the CEO of Anthropic, The Adolescence of Technology, and he talks about a world where we have a data center full of Nobel laureates, where you could have a data center with bunch of Nobel laureates, and you could go and ask them anything, or you can go and ask them to solve any problem. So, like, if you imagine a future like that, I think it's like you could get an answer to anything you want in like maybe an hour. So I like to think of this as like a centaur model. There's a research from Harvard that calls like this pattern like a centaur model where humans more and more like co-work with AI and both generate solutions together. I would like to think of the future of the world in that way rather than AI doing everything and humans not doing anything. So I don't know like how it's going to shape out, but that's just my view on it. Uh, so comparing this to the Industrial Revolution, so this is a very interesting topic which uh, uh, like Dario Amodi also talks about in the essay. And so AI is a general purpose technology, just like the steam engine, but one of the key differences is that it's rapidly evolving and people are using AI to accelerate the development of AI. So this creates like a very interesting feedback loop that we've never seen before with previous technologies. And the pace of progress is like staggering. So you've seen like AI go from barely able to write a single line of code to like write an entire code base in like 2 years. And the steam engine took like decades to spread across different industries. It was very physically it had to be placed or uh, it had to be deployed. But AI can just be instantly deployed everywhere, and it can be upgraded in one go. Like you can go from ChatGPT 4.5 to 6 in like a configuration change. So so that's kind of different with AI. And the other thing is in the Industrial Revolution, there were people who were displaced in farming, let's say. They had another field to go to. Let's say they went from farming to doing maybe like a clerical job because they're totally unrelated industries. But with AI, the disruption is happening across the sectors. It's happening in finance, it's happening in law, it's happening in consulting, it's happening in customer service. So AI is just generally getting better across the sectors. So here the risk is that, if you get displaced from one sector, you go to another sector where AI has already become better. And I don't know like how that would shape out for like the labor markets or the world in general, but this is something that is different, like with this kind of uh, world that we live in now. And the similar point to that is that it impacts people not by the profession they're in, but by their cognitive ability. So if you're like cognitive ability level 1 or 2, it's going to impact you the same, irrespective of which field you're in, versus your cognitive level 5, 6, 7. You might because AI's cognitive level will keep increasing everywhere in all the sectors. So you're basically competing with this. I mean, I don't know if I should say competing, but like you're basically trying to work with this like system that's increasing its ability across the board. So I don't know how things will shape out in terms of people getting displaced. Maybe they'll just do more work and there will be more projects and more productivity. That's one way to look at it. Or there could be like maybe a lot of displacement. So I would recommend this essay. In this, he thinks about this topic very, very extensively. And I think he talks about a short-term kind of shocks to the labor market in the next 1 to 5 years, where there could be some like amount of displacement to like entry-level positions. So it's good to be aware of like the future. Um, so some key takeaways here. So I think we covered a lot of ground. I think we looked at how scale of models beats handcrafted solutions, how transformers changed the whole landscape, and then models became uh, from very specialized models to more general models that can do a lot of things, and then the foundation building blocks of agents and how they all work. And the technology, yeah, it's powerful. There are challenges, and the future of work seems to be more related to supervision and not execution. And yeah, I think you should start using it for your projects, see where it is useful, try to see how you can work with AI versus against it, and uh, make it uh, make it like work for you, build it out in a way that it works for whatever you want to achieve. And yeah, I I'm excited to see how it's applied in the datathon as well. So yeah, thank you. Feel free to connect with me, and I think we're almost like at time. But yeah, if there are any questions, happy to.
Thank you so much. That was so helpful. I think it was extremely relevant for the time right now. If anyone has any questions, feel free to put them in the chat, or you can use the raise hand feature and we will call on you. I have one question to start off. So I know you're an applied scientist. Could you kind of explain what that role kind of looks like and how you use AI in your work?
Yeah. Are you still recording, or do you want to?